All right. Hello, everyone. Welcome back to the HoTTEST Summer School. This is the eighth lecture overall. It's the fourth lecture in the Agda series. We're very happy to welcome Dan Licata, who is going to tell us about higher inductive types. Thanks, Dan.
All right. Thank you for inviting me, and thank you for organizing this great school. I'm really happy to start to meet all of you and happy that you're excited about this field of research. So what I want to do in these 4, 5, 6 Agda lectures is to talk about something called higher inductive types, which are one of the new ingredients in homotopy type theory that weren't there in sort of exactly the same form in earlier type theories. And along with univalence, which we'll get to in a little bit, those are kind of the main new things that you add to the kind of Martin-Luff type theory that Martin was talking about in the first 3 Agda lectures to get to homotopy type theory. And so my rough plan, which is subject to change depending on how fast this goes, because I'm always pretty bad at predicting that until it's live, is to do some examples and what's called the non-dependent elimination rule for higher inductive types in this lecture, and then to do the dependent elim and prove some type equivalences in the next lecture, and then do calculating the fundamental group of the circle in the 3rd lecture that I'm giving. But some of that might move up. We might get to fundamental group of the circle in next time, depending on how things go. Okay, and we've got a bunch of exercises for you to do afterwards, which are really just like getting your hands on these higher inductive types and playing with them in Agda. So before we get to the Agda, I just want to do a little bit of pictures to kind of illustrate what higher inductive types are for. So in HOT, we think about types as infinity groupoids. You've seen this a bunch of times now earlier in the school. That means that types have points and types have paths and types have paths between paths. Like here's a homotopy or a path between paths connecting P and Q, and so on, sort of all the way up. And the regular inductive types that you've seen in Agda before, like the Booleans or the natural numbers, are types generated by point constructors, in the sense that for Boolean, you say it's the least type, the free type containing true and false, which are points, or containing 0, 1, 2, 3, 4, 5. Okay, you present that by a function successor, but picture natural numbers, it looks like that, right? There's a bunch of disconnected points there. So what we do when we start to introduce higher inductive types is we think about types that can have point and path between path and so on all the way up constructors. So you have a type that's generated by giving constructors for not just points, but also paths and paths between paths and so on. And so the first example of this, which we'll use to kind of introduce the concept, is the circle. So if you want to present the circle in type theory, you can present the circle as a type with a point and then a loop, so that you think of it as, kind of visualize it like that, as making a circle. And as a type, we'll think of that as a type where we have a constructor base that constructs an element of the type, and then a constructor loop that constructs a path on the type. And this will be clearer when we get to types with more than one points, but the path is sort of directed, but it's not, in the sense that this sort of has an orientation and that it goes one particular way, but then there'll be other paths like loop inverse that would represent going backwards on the circle. And so we can form other paths out of the groupoid operations, which you've seen in, I think, both the tracks by now, which is like composing paths, concatenation of paths, or symmetry let you make new paths. So we're going to get to all of this again in Agda in a few minutes. This is just sort of a preview of what's going on, and then we'll start to deepen that a little bit. Is there a question at this point, or not yet? Okay. Anyways, just for the whole next 3 lectures, feel free, anyone, to jump in at any point with questions. Like, I would totally appreciate that. So before we really dive into doing the circle, I just want to show a few more examples of higher inductive types. And I don't expect you to like understand all the details here or see what, is really happening. It's just like, if I'm going to introduce this new concept of higher inductive types to you, I want to motivate, why are we interested in it and what kinds of things can you do with it? So one thing that we'll get to later today, I hope, is to talk about a different way of presenting the circle, where instead of a point and a loop, you have 2 points and then 2 loops. I'll call them east and west. And then the idea is that we'll work towards proving that this definition of the circle presents the same type, the same infinity groupoid as the one where you only have 1 loop. And the idea is that, maybe I should have drawn my loop going the other direction, going clockwise, but then the idea is that, for example, the loop might be going around like that. So like by going down along the east and back up along the west, you would get a loop on the circle. And so up to homotopy, that should be the same type as this one. Another space you can present that we'll use in the exercises if we get to it is the torus. So the idea of the torus is that if you've got a donut here, you can present it by a type with 2 loops. So I'll call it P goes around that way and Q goes around that way. And then as constructors, that says this type has a point and it has a path, just like the same kind of path from base to base that we saw on the circle. But then it also has something else, because on the torus, you don't just have the one path that I called P there, you've also got another way that you can go around the circle. And then these have the property that if you go around that way and you go around that way, that's the same as first going around that way and then going around that way. And that homotopy you kind of think of as the surface of the torus there. And so when we do it in type theory, we'll do it by saying that there's a path between paths between first P, then Q, and first Q, then P. Okay, so for those of you who are coming from more of a math background, if you've seen suspensions before, suspension is a general operation on types, which lets you say that you've got a type A here, and then you add 2 new points, you add the north and the south, and then through every point in A, you add a path from north to south. So for example, if you take a circle, add a north and a south, and then start adding paths to every point on the circle, what you get is the 2-sphere. So the suspension type, which is also a higher inductive type, is a way to make spheres. You can define the n sphere by iterating the suspension n times. Anyways, we'll get there later. Presenting this, you've got 2 points, but you've also got a path constructor that adds in a path between north and south for every element of the type A. And then for those of you who have some category theory background, you can do push-outs this way. So push-outs are a pretty fundamental construct in a lot of the kinds of stuff we do in homotopy type theory. And so the push-out type is another example of a higher inductive type, where you take a copy of A, you take a copy of B, and then for some other type C, you have functions from C to A and C to B. And what you do is you glue in paths from the image of an element X here. You look at its image in A, you look at its image in B, and then you glue in paths between those when you're making the push-out. Okay, so we'll come back to these maybe in some of the exercises or some of the future lectures. The point was just to say that like there's a lot that you can do with higher inductive types. And so what I want to do really with these next 3 lectures is just get a feel for that, and also to get a feel for what it looks like to do these things in Agda. And then after I do that, I think in the next lectures, the 7, 8, 9 Agda lectures, Anders will show you a little bit about what it looks like to do these things in cubical Agda, which is actually even nicer. But it's nice to do them in axiomatic HOT, in book HOT too, and I think it helps you get a feel for what these things look like. Okay, so anything to talk about before we switch to Agda? Okay, I am switching to Agda. Okay, so if you do a pull on the repository, hopefully you will find that there is now a HoTTEST directory. So HoTTEST stands for higher inductive type. So hopefully you will find that there is now a higher inductive types directory inside of Agda. And if you look at the new prelude file first, just to get oriented, we don't have to read through the whole thing. So this is all stuff that I copied from the previous lecture's developments. So I think you've seen everything in here, maybe slightly renamed in a few cases. But using the material on universe polymorphism from the last Agda lecture, I've upgraded everything that we did in the lectures 1, 2, 3 that I'm going to use today with universe polymorphism. So for example, the identity type triple equals there now takes a level parameter and works for any universe level, and the path concatenation operation works on types of any level, and so on. For the inverses in the previous lectures, it was called inverse. And when we're reading the Agda goals, I tend to prefer a prefix notation. So in lots of the Agda hot stuff, we tend to use a prefix bang for that. So I'm using that convention rather than the inverse. So prefix bang is inverse. We'll see examples in a second. Anyways, so hopefully all of this stuff is stuff you've seen. I don't know. Did you get to do the equality chain stuff in class, or is that just in the notes?
I don't believe we've done it in lecture.
Okay, so then I know that was in the repository and you might have used it in the homework, but if it wasn't in lecture, then I'll go over that when we get to it. Okay, so you can find some stuff here, and we can collectively copy some more stuff in and make it universe polymorphic if we need it. But this wasn't an attempt to be a comprehensive edit of the repo, but just a self-contained file with universe polymorphic definitions of everything that I'll need today and that you should need on the first exercise sheet. Okay, so that's that. And so beyond that, if you want to follow along and you want to look ahead, lecture 4 notes is what I plan to do some subset of today. So this is like the end of the class. And then if you look in lecture 4 live, then this is where I'm going to type some stuff. And I just checked in a stub. So if that push went through, then you should have this file if you want to type along. Okay, so any technical issues getting oriented that we should sort out here? Okay, let's define a higher inductive type. So let's do the circle. So Agda, but by which I mean like book hot, axiomatic hot Agda, doesn't have support for higher inductive types built in. So we're going to kind of have to make it up as we go. And so what we're going to do is we're going to use something called postulate. And we're going to postulate, for example, that S1 is a type. And postulate is basically like, conceptually, the way to think about it is that you're making the whole rest of the development depend on a variable S1, which is, in this case, a type. So if I didn't have inductive types, I could, for example, start like postulating constructors bool, which is a type, and true and false. This won't actually load because true and false are already defined in the library, but you could start postulating stuff like that. And so at this point, you haven't said yet that it's inductive. You've just said that a type named bool exists and a constructor named true exists and a constructor named false exists. And when we get to cubical Agda, we'll actually have a syntax for writing down higher inductives kind of inside Agda. But for these 4, 5, 6 lectures, lectures 4, 5, 6, we're just going to use postulates to make these types up. So if you remember the picture from before, the circle was a type with a point and a loop at that point. and we'll use the identity type, the path type, the identification type, whatever you want to call it, to make the point and loop. So here I'm saying, please assume that the rest of the program has a type named S1 and a base and a loop. And it's a little bit too much to type live. Like if you want to be fancy, we could write S1 in like a bold S with a superscript 1. I'm just going to use the regular ASCII version for today, but you can kind of deploy your Unicode to make it look pretty if you want. But I'm just going to go with regular ASCII there. Okay. All right, so that makes the type S1 exist. It makes the base point exist. It makes the loop exist. And I added a little thing where sometimes I'll write things like that. And so what that's doing is it says the brackets there are just letting me add a type annotation to the path if I want to emphasize what type this path is in. And here it's kind of silly because you can read off from the fact that base is a constructor of S1 that it's in base equals base, but sometimes it's handy to emphasize that. All right, so any questions about the postulates there to get S1 going?
We have a question in the Q&A, which is, how do we know our postulates are consistent?
We don't. I mean, but like, how do you know your variables are consistent, right? So like, if you write some module and you put in, or some function and you put in a bunch of assumptions, then like, you don't know that those assumptions are necessarily satisfiable. So there's nothing in Agda that checks that your postulates are consistent. But like for these particular postulates, we look at models of homotopy type theory and papers on semantics of higher inductive types, and say that we can interpret these particular constructors in particular models. Does that help? Okay. Okay, so now let's write an example path. So a loop on the circle is going to be a path from base to base, an identification of base with base, of equality between base and base. And so what we can do is we can use things like path concatenation and path inverses to define paths from base to base. So for example, say I want to go forward on the circle and then backward on the circle, right? So if forward is, I don't know, clockwise, then I'm going around this way, and then I'm going back around the other way, then that would be loop dot loop, because this is composition in diagrammatic order, which means you first go along this path, and then you go along that path, and the bang loop is the loop inverse. And then if I wanted to go, I don't know, forward again, and then backward again, and then forward again, and so on, then I can write stuff like that. So the thing I'm trying to emphasize here is that we said S1 is a type with a loop constructor, which is a path from base to base. But you don't just have the paths from base to base. You also have all of the other paths that are generated by the groupoid structure and infinity groupoid structure on types. So the concatenation operation of paths on the circle comes because every type has a concatenation operation. The inverse operation of paths on the circle comes because every type has an inverse operation, and so on. And so we're putting the circle in a nice way because the rest of the structure of the type theory gives us a lot of structure on all types that in particular applies to the circle. Okay. So now what I want to work towards is showing that this example path has a path between paths to the loop, right? Because we consider types up to homotopy, or in this case, we're just talking about like a one groupoid. And so what we're saying here is that in a groupoid, so maybe those of you who have a background in abstract algebra, like a groupoid is sort of like a group with types. So you should expect that in particular, when you look at the loops at a point, it really does behave like a group because you don't have any interesting types involved. And so the, for example, the concatenation should be like a group multiplication, the inverse should be like an inverse. And so if I have element, element, inverse, element, element, inverse, then that cancels and just gives me the one at the end there. And so what'll happen is that we should be able to construct a path between paths, that is a path in a path type in S1 that connects this to loop. And so what I want to do for a while is to define the groupoid laws.
Dan, there's a question that you're necessarily going to get to soon, but just as a preview, is loop distinct from REFL? How does Agda know this?
Okay, that's a great question. So right now, if we've just said there is a type, there is a point, there is a loop, there are models of that in which loop is REFL. Like you could interpret this where S1 is just the unit type. There are models of these postulates that I've got on the screen where it's actually like not REFL. And so we don't know that yet. So to distinguish the two inside of type theory, we're going to need a few things that aren't on the screen yet, which is one, we're going to need the elimination rule for the circle. So in previous lectures, you saw like the elimination rule for Booleans or the elimination rule for natural numbers. There'll be a corresponding elimination rule for the circle that says that it's the initial type generated by this data. So we haven't even said that yet. So we'll need that, number one. And then we'll also need univalence, I think, to distinguish those two. But by the end of what I hope to get through in the next few classes, where we prove that pi1 of S1 is Z, pi1 of S1 is going to be defined in terms of the paths from base to base, and then loop under that equivalence with C will correspond to 1, and REFL will correspond to 0. And then because it's an equivalence, you'll know that it's injective. And so because 1 is not equal to 0, you'll be able to conclude that loop is not REFL. But it'll take us a little while to get there. That is a great question. Any other questions to do now? Okay. Oh, I just peeked and saw this in the chat. So if you're in Emacs, I think the magic keystroke is Control-U, Control-X equals is the magic keystroke that I can usually remember. So that's Control-U, Control-X equals equal sign for bringing up how to type some of these symbols. So if you open up the notes file and do that on a character, you can figure out how to input some Unicode stuff because it'll report how to type it with the Agda input method. Or you can do what I sometimes do, which is just find a file that has the character in it, copy it, and paste it every time. Cool. Okay. All right. So now let's make some groupoid laws. So I think you at least, did you state and prove some of the groupoid laws in the HoTTEST lectures? Have you seen those? Or did you just do concatenation and inverses? Well, let's do them again because, oops. Okay. So for example, let's prove associativity. So if A is a type, so I could make this universe polymorphic. I'm not going to just because it's a little bit easier to do it and I'll only need it for the first universe right now, but these could all be made universe polymorphic. So suppose that I've got X, Y, Z, W And then I've got P, which is a path from X to Y. And then I've got Q, which is a path from Y to Z. And then I've got R, which is a path from Z to W. Oops. So for these Unicode ones, if you continue typing, sometimes that's like another symbol. And so what I usually do is I type the Unicode character, then I hit space, then I hit backspace. And so the space there kind of dumps it out of Agda input, making another character mode. And so what does it mean to state associativity of path concatenation? It means that P then Q, let's see how I did it, then R is equal to P then Q then R, right? And now these are paths from X to what? W. And I'll need some parentheses there. Okay, so any questions about how to state things like that? Right, we've seen that in the hot track, but in Agda it just looks like assume some paths PQR, and then you get that this path is equal to that path. By the way, these are paths from X to W, and then that's in the type A, and this holds in an arbitrary type A. Okay, so the nice thing is, once you've stated a law like this, you're essentially done. Because for a lot of these things, you can just prove them by path induction. So what I'll do to prove this is by path induction, I could, for example, assume that all three paths are reflexivity. And then, well, if I do that, then what do I need to do? I need to give a path from reflexivity to reflexivity, which is just also reflexivity. So if you want, you can fill in that this is like you could give a name to that one, and then this one and this one are forced to be that one. And so you put a little dot in front of those in Agda. But really, the way to not think about it too much is just like when you state one of these things, what I tend to do is I just start matching on stuff as ruffles and then see how far that gets me. And then this one is actually reflexivity on reflexivity, right? You can fill that in, but Agda's pretty good at filling all that in. So don't think about it too hard. Way to do these is you just fill in reflexivities and then, see how far that gets you. And then hopefully it gets you far enough that you can just fill in reflexivity as the goal. So path induction not only gives you concatenation and inverses and so on, but by proving things, by constructing a path between paths by path induction, you can use path induction to get the groupoid laws there. So as another example, I don't know what to do. If I'm going to do the unit law that says for any type, for any xy in that type, then if I have p from x to y, then the left unit would say that reflexivity then p is p because the left unit is supposed to say that reflexivity is a unit for concatenation on the left. Okay, and so what does that look like? Well, we can put in a variable p, but then we can say, hey, by path induction, let's just assume that p is ruffle. Now I've got the composition of reflexivity and reflexivity, which just definitionally reduces to reflexivity. And so, well, if I need to show that ruffle is ruffle, then ruffle is a good proof of that. So the way that you do all of these is you just state it and then do path induction, at which point it reduces to reflexivity, and then you fill in reflexivity there. So I think I'll copy in the others just from the notes file, just because it's a little bit boring to type them all. Okay, so let's read the right unit. So the right unit says that for any path P, P then reflexivity is P. And so we could do this in the same way as we did the left unit by replacing that with reflexivity and then saying, oh, that's just a path from ruffle to ruffle. So that proof works too. It turns out that if you look at the goal, this one holds by reflexivity on P without doing the path induction. And the reason for that is because there was a little bit of a bias in the definition of composition in the previous lectures, concatenation in the previous lectures, where where's this? Definition of composition in the first place said that, where'd it go? There it is. Okay, right. So there's a bias here. When you're defining composition, I think you saw this in the hot track, you can do it a couple of different ways. You can define it by path induction on the second path, the y equals z. You can define it by path induction on the first path, the x equals y, or you can define it by path induction on both of them, and then you get different but homotopic proofs of that. This library has it set as a definitional equality that P then ruffle is P, and so that's how it works out there. So in that case, sometimes you don't have to use the unit law. So this is nice for like the practice of formalization. It can be a little aggravating, like conceptually, because like sometimes it's, you end up thinking about, well, like maybe I can arrange things so that it's a right unit instead of a left unit, even though those are morally like kind of the same kind of thing, because hey, then I get better definitional equalities. But that's a thing you can do. Okay. And so then the rest of the groupoid laws are, let me copy those in too, so we can just read them. The inverse law says that for any path P, if you do go along P and then along P inverse, that's the same as P, and the left unit law, so I'm naming these after like unit L means the ruffle is on the left, unit R means the ruffle is on the right, inverse L means the inverse is on the left, inverse R means the inverse is on the right, means that if you go along backwards along P and then forwards along P, then you go back to ruffle.
Dan?
Yes.
There's a question. So
great.
You are pattern matching on all in ASOC on all of P, Q, and R.
Mm-hmm.
Why not just leave some of them?
Okay, let's try. I don't know. Great question. Okay, so let's suppose we pattern matched on none of them. Then what we have to prove is that PQR is PQR. And because of the associativity that's set on, let me find it, this line, so this infxl syntax just makes this left associative. So that means that when you see PQR, you parse that as PQR. Okay, so if we match on none of them, then, well, okay, we didn't make any progress, right? So this one is not true definitionally. We could start to match on stuff. So maybe I start to match on R. You can get Agda to do this for you. I'll sometimes do this. If you put R in the goal and then you do Control C, it'll match it for you, which is a little bit faster than replacing it and reloading the file, but that's not like just, if that's hard to remember, just write it yourself, it's fine. Okay, so now we can see, well, how far did we get? Hey, that worked, right? Because if we match on R, because the right unit is the identity, definitionally, what's happening is that when you turn R into REFL definition, then this definitionally turns into Q, and this definitionally turns into P then Q. And so we can just fill in our reflexivity on P then Q. There is the answer. So yeah.
So one observation is that this would not have worked on matching on any other of the variables. And that's because you have an asymmetrical computation law when you were defining path concatenation. And that's sort of, I think, not ideal. If you're exploiting the fact that it computes on one argument, but not on the other in the course of a proof, the more ethical approach, in my opinion, is to define concatenation by fully pattern matching on both arguments so that you couldn't do this.
Yeah, there's arguments either way. I mean, like I certainly have big Agda developments of synthetic homotopy theory where I'm sometimes careful about like trying to get things to be definitional. I mean, in principle, it doesn't matter, but in practice, it can make a big difference in how aggravating things are to do. So yeah. So like this one now, right? So like if we'd matched on L, well, we can't just do reflexivity here, but we could try to do something with the unit laws, right? Because if I'd already proved the left unit law by this path induction, then I could try to use that here to collapse the REFL then Q or the REFL then Q here, REFL then QR on this side or the REFL then Q on that side, right? So there's different ways to do these things. Kind of the maximally, like the thing that, you know, sort of gets you there fastest is usually just like pattern match on everything in sight, do path induction on everything in sight. But then that also, you know, sometimes has worse definitional behavior down the line. I wasn't really planning on doing too many examples in these lectures where we reason about these homotopies, though there's one of those on the exercise sheet. If you're doing that, then sometimes it can be handy to tune the definitional equalities. Yeah, that was a great question. Any other questions? Okay, so if we go back to the chase, the goal was to show that that example path, and let me just expand this out just because we're gonna want to read it. Okay, the goal now is to show that okay, what we would like to do is to deploy all of the above to construct a homotopy between loop, then backwards loop, then backwards loop, then loop, and loop. And I want to use this to kind of illustrate a way of doing some path algebra, is kind of the jargon for like, you get to a point in a proof and it's just path algebra, means a bunch of like applications of the above lemmas. And so this is kind of a typical, like, kind of boring, but you have to do it. Part of synthetic homotopy theory is you end up doing a lot of like manual calculations like this. Okay, so what I'm going to do is I'm going to use the equality chain stuff, which I don't think we've done in lecture, I'm told. So that's these operations, and I'll just show you how to do it. And if you're following along, you could just copy this in. Like, I'm not sure that typing this one yourself is really that instructive. It's in the notes file, and you could just copy it in. But the way we're going to use this, which is handy for a bunch of things, is that we get something on the screen and then I'll talk about it. Okay, so what the equality chain syntax lets you do is it lets you write out in a nice way a composition of paths that is a transitivity of equalities, where you're doing a deduction. I mean, it's like a 2-column proof. You're doing a deduction that this equals this equals this equals this. And then at the end, you get to like the thing you wanted. So Agda is going to color a bunch of stuff because it doesn't really understand where I'm going in the middle of this yet. But what you can do is you can use this to kind of write out some intermediate steps. Like, for example, say my first step is to emphasize that, oh, which way is this associated by default? It looks like that way, right? So like, say I want to record for the reader that it looks like that, then I could use reflexivity, right? Because those are actually definitionally equal and in fact syntactically equal, because this is just how this go forward, go backward, go forward, go backward, go forward gets parsed is just like this. Say I want to just associate it like that, then I'll write it like that. Okay. And so the way I tend to program these is I'll be like, okay, copy that line, paste it in, and then, you know, figure out, okay, what am I doing next? Maybe I want to kill that loop, then loop inverse, and turn that into a reflexivity. And then oops, ruffle underscore, right? So then I say, okay, I'm going there. And then I say, okay, what's my next step? I'm gonna first contract that this loop, then loop inverse by the inverse law is reflexivity. And then next, I'm gonna use a unit law to get it looking like, say that. Is this the one that I did? I'm not sure that I'll end up with the same path that's in the notes. We'll see. Okay, and so, right, so after I contract the unit law there, then I get that it looks like forward, backward, forward again, right? So which is that step. And then, okay, I mean, this is kind of gratuitous, but just to illustrate using associativity, say that I want to now reassociate it to look like that. Then I can reassociate it to look like that. And then I could collapse that unit law like that, and so on. Okay, and then be there, right? So the nice thing about this notation is it lets you write out a composition of steps where it gives you a place in the file to record what the endpoints are in the middle of the transitivity of the paths, like the composition of the paths in a nice way. And so I don't always do this, like, as you know, somebody who's been hacking in Agda for many, many years now, like I'm pretty want to just like bang out the proof without writing it down the steps and see Agda. But this is a lot more readable if you want to like show it to someone after the fact, because you can kind of read the steps. Like first I collapse this loop, then loop inverse, then I collapse this unit, then I reassociate, then I collapse this loop, then loop inverse, then I you know, collapse this unit, and so on. Okay, and so then once you've written out what you think is all the steps of the proof, then you can start to fill in the reasons why, and those go in between these angle brackets. So this symbol is the same equality as the path, and then backslash Langle, I think, is the way to type this one. Oops. Yeah, backslash angle or backslash Langle or backslash comma are ways to type that thing in. There. Okay, so then now our goal is just like in each bracket to fill in the reason why the two things in between the bracket held, right? So like, why is loop then ruffle loop? Well, okay, that one, in fact, if you want to peek, is ruffle, or the fancier version of ruffle that it is its composition unit on the right on loop. Okay, good. Questions about the setup here, or what we're trying to do?
Dan, now that you've split it into several steps, which you're going to say what happens between each one, how successful is auto in being able to fill in those steps?
I would guess not very, but I actually never really use auto, so I shouldn't guess that too strongly. But
well, let's try.
I don't even know the keystroke for it. Does anyone know?
CCCA.
Control C, Control A. New solution.
Okay, not very successful.
Yeah. So auto, like, I don't think, okay, so like my knowledge of auto is probably from about 2012. So like, I shouldn't say too much, but I don't think auto will really like backchain and like try to use lemmas that you've established to prove stuff. I mean, there are ways to write solvers in Agda, but I don't think auto is like, you know, tactics and some other proof assistant, if you've seen that kind of stuff where it'll.
Oh, someone in chat says that you need to use a macro to input lemmas that can be used in auto.
Yeah, okay, right. So like, I think there's ways to nominate things for use in auto. That does sound right. But thank you for that. But like,
oh, actually, there's another very interesting suggestion. If you just go to the first hole and you type in /m, -m, no, -m, and then try CCCA, that will use lemmas.
Okay.
Is what someone in chat claims.
Okay.
CCCA on that?
Yeah, I'm trying.
Nope.
Yeah, so I think we need to install the particular lemmas. Yeah, so this is a good topic. What I want to do is to show you like explicitly the proofs that it'll find. And one of the reasons I want to show you that is that sometimes when we get to things, I'm not sure we'll get to this in these lectures, but sometimes when you're constructing these paths, you do actually care about like which homotopy you're picking here. So like sometimes it'll matter that like you pick a particular proof of this equation rather than just any proof of this equation. So you do need the skill of being able to write down these things yourself, even if we could install some things as lemmas and get auto to find it. Yeah, that's a cool topic. Let's explore it in a little bit. Okay, so what do we want to do to collapse? I don't know, which one do we want to do? Maybe this one. Okay, so this one's not so bad, right? That should just be associativity, and then you can kind of look up and see for associativity, I'm going to let Agda fill in the type. I'm going to let Agda fill in the endpoints of the type, and then what I've got left is to fill in the paths here, right? Okay, so you could try putting in underscores and say, oh, can Agda figure that out? And then you load it and it changes color, which means no, Agda didn't figure it out. And so at that point, you can start to fill in some of them. Like maybe if I put in one of the paths, then that's enough for it to guess no. Maybe if I put in two of the paths, oh, I'm supposed to be going, okay. Let me go back to that. Okay, you can start to see what it figures out, and then, okay, maybe it didn't. Let's just do that to see it. Okay, so that looks kind of right, except what? Like my associativity lemma turns a right associated thing into a left associated thing. And it turns out that my goal is turning a left associated thing into a right associated thing. And so I've guessed the right lemma, but I didn't tell it to go in the right direction. And so you can do it that with a inverse, right? So I'm taking the inverse of a path between paths to point it in the right direction. And then I think we can leave out that one and it'll still figure it out. It doesn't like leaving out that one. And the reason is whichever things it matches on, it's not going to like leaving out, because if it matches on it, then there's more definitional equalities and unification will not figure out that that's a thing that can leave out. So we can probably leave out those two, but we need to stick in the last one there explicitly. Okay. So what I'm doing is I'm applying one of those previous lemmas, right? I said that paths have a groupoid law, that's the associativity. I'm applying the previous lemma, but I'm kind of doing it in a different direction, right? So I'm using these path operations there. Okay, good. Questions on that step? Okay, so now what about filling in, question. Oh, somebody raised their hand, but maybe that wasn't a question. Okay, so what about filling in this step? What should we do? Well, what we want to do is we want to do the left unit law for a loop, which should say that, right, so if you look at the have part, that's telling you what you have. It should say that the, oops, sorry, not the unit law, the inverse law or loop, which says that if I go backwards along the loop and then I go forwards on the loop, that's the same as ruffle, right? That's what we want to use there. And that's good, except does this exactly match our goal here? Not really, because we're turning this into this, but with this bit stuck on the front. And so what we need to do is we need to apply this path in context. And the way that we do that is with the app here, which is what says that if you have a function and then a path from x to y, then you get a function from f of x to f of y there. Okay, so we'll use app as a congruence principle to say that what I want to do is take the context loop then whole and stick that around both sides of bang in vel, because the bang in vel says that loop compose loop is ruffle, and then the app says, okay, stick a loop on the front of that and a loop on the front of that, and then what you get is that this term is equal to this term there. So hopefully that'll load there and we get that. Okay, so this use of app is sort of like saying, okay, if I know that x equals y, then I know that f of x equals y. And here I'm writing down my f. And you can write the functions with like an explicit lambda there, kind of typing / lambda to get the Unicode, but you can also type it with just a \, and I tend to like prefer the \ for the ones that are near app and stuff, because I kind of want this thing to be emphasized without the lambda there. Like I almost want app to take a binder of nh there. Okay, questions about that much? Good. Okay, and that's kind of how the path algebra goes. So let me copy in the other ones and we can just read them. Okay, for the first one, hopefully I did the same as in the notes. Okay, window needs to get bigger. So what we're doing in the first one is we're doing the right inverse on this bit with the context, all of this stuck there. And so you can kind of do this just by like copying and pasting the context and putting a h for whole for the spot where you want to apply the rule. And then you do that to turn that into that. And then for the next one, what do we need? We need to in the context with a loop and a bang loop, with a bang loop and a loop stuck in, then we want to do what the left unit for the loop there. Okay, good. All right, so this is a nice example of some path algebra. Good. Any questions on that bit? All right, so the next thing to talk about is what's called circle recursion. So the circle is a type with a point in a loop. What circle recursion is going to say is that to map from that type into any other type, what you have to do is you have to find, oops. Okay, to map from that into any other type, this is the data for the circle. What we want to do is we want to find the image of that data in the other type X. Okay, so the circle is a type with a point and a loop. To map from the circle into some other type X, you find a point and a loop in that other type X. And the idea is that that sends the point of the circle to this little x, and it sends the loop of the circle to this little l. And so then what's going to happen is that, for example, if I have this data, then that determines a function from S1 to X. And if I apply that to the base of the circle, then that should give me back the point that I chose. And the other reduction rule is going to be that if I'll just put quotes around this for a second, and then we'll make sense of it. If I apply this to the loop on the circle, then I should get out the loop L that I picked there. So for Booleans, you saw if then else, which said, okay, I'm going to send true to this point of some other type and false to that point of some other type. And that was the non-dependent elimination rule for the Booleans. This is the non-dependent elimination rule for the circles. Rec is kind of just the keyword that we'll use for non-dependent elimination rules. If then else sent true to the point you picked for true, it sent false to the point you picked for false. But here for the circle, we're going to say that the circle lim is supposed to send base to the thing you picked for base and loop to the thing you picked for loop. Okay, so that kind of makes sense conceptually. Any conceptual questions there? What we need to do is we need to make sense of this. So we can't literally apply S1 rec to loop, because S1 rec with X and L fixed is a function from the circle into something. Loop is not a point in the circle, it's a path in the circle. So what we need to do is we need to apply it to paths with the app thing, which is saying I want to apply this function not to a point, but to a path. And so one reading of app is that it's the apply to paths function. So it takes a function and applies it to a path rather than a point. And so what we want to do is we want to say that this gives us back the L that we started. And so one problem is that we can't literally say that this is L, because the type of the left-hand side is the function out of the circle applied to base is the function out of the circle applied to base, and the type of L is X to X there. And so what are these off by? They're off by this reduction here that says that S1 rec base is S1 rec on base is X there. So one thing we could do is we could compose with this path to state this equation, but there's another trick we can play, which is to use some rewriting magic in Agda, where we would say, we need 2 lines. We're going to say built-in rewrite with equality. And then we're going to say, I would like to rewrite on S1 rec base. And then if we postulate this thing, then what the rewrite magic does is it tells Agda to apply this as a definitional equality in particular this direction. So it's like, please reduce S1 rec XL base to X whenever you see it. And so if you do that, then this goal has the same type as L. So this rewrite stuff was added to Agda relatively recently. In fact, the first version of it was implemented in part by Guillaume Brunery to do exactly this, to let us like add in a nice way definitional equalities for higher inductive types. Okay, so what happens then is that this is actually a definitional equality, and this is what's called a typal equality, a path, a propositional equality. And we won't make this one be a rewrite. You could, but it doesn't end up being all that useful in this kind of setting because you end up doing a lot of the path reductions by hand anyways. But when you get to cubical type theory with Anders in a few weeks, then this will in fact be a definitional equality in cubical Agda. Okay, so that was kind of abstract because I wanted to boot stuff up. So what I want to do now is to define a particular function on the circle so you can start to get a feel for how this works. So let's write the function from S1 to S1 that if you think of the paths on the circle, maybe if you're coming from a math background, you know this already, then there should be Z many paths on the circle where the loop is 1 and loop composed loop is 2 and loop inverse is -1 and refl is 0 and so on. And so we can think about the function on the circle that doubles a loop, meaning it sends the n loop to the 2n loop. And the way we can define that is we'll do an S1 rec. And Agda then tells us that when we do an S1 rec, what we need to put in is a point of S1 and then a path in S1 from that point to itself. And of course, there's only one point constructor on the circle, so we'll put in base, not too much choice there. But here, what we need to do is we need to give a path from base to base. And so we could fill in, I don't know, loop there, in which case we'll get the identity function. But to double loops, right, what do we want to turn 1 into? We want to turn 1 into 2, right? And so this is the function that sends the circle to itself by when you go around the loop once in the domain, you go around the loop twice in the codomain. And so now I want to do some examples to kind of calculate that this is the right thing. We can check that, for example, if I apply the double function to the loop, then what I get out is 2 loops. And well, why is that? It's because this is an S1 rec applied to the loop. And so, hey, that S1 rec loop constructor just says that that's what's supposed to happen. But what I want to think about now is, okay, what happens if I double 2 loops? Like say I apply double to the path on the circle that already does that, then what should I get? Well, 2 times 2 is 4, so I should get something that looks like that out there. So the question is, how do I prove that, right? I've got my function. It's defined on the circle by saying that it takes loop to 2 loops. How do I then prove that it takes 2 loops to 4 loops, right? I didn't say that explicitly in my definition of my map out of the circle. And it didn't say, oh, here's the case for what you do on a composite, and here's the case for what you do on an inverse and stuff like that. And the reason is that it's determined because all functions are going to be group homomorphisms or functors or however you want to say it. So in general, we can prove that, let me copy in some of it. Okay. Suppose 2 types A and B, a function from A to B, and 2 paths that are composable P and Q. Then what do you get if you apply the function f to P then Q? Right, so like you can set up this goal that's just like, okay, suppose I've got P, which goes from X to Y, and Q, which goes from Y to Z, then app f P then Q is a path from f of X to f of Z. And this is the situation we're in down here because app double loop then loop is of the form app of some function on a path then a path. And so what you can do is you can kind of think, okay, is there anything else that also has this type made up kind of generically out of these ingredients? And then ask the question, well, are those 2 equal? And usually the answer is yes. So what else has this type? Instead of composing P and Q and then congruencing f onto both sides to get f of X equals f of Z, I could think about what happens if I stick f onto P. Well, then I get a path from f of X to f of Y, which is helpful. But it leaves me needing to go from f of Y to f of Z. How can I go from f of Y to f of Z? I could stick f onto Q, f onto Q there. And so that's a conjecture about what happens when you app f onto there. How do we prove such conjectures? Well, just do some pattern matching to do path induction and reduce everything. And then, hey, yes, that worked, reflexivity. Okay, so by doing that, we can get a rewrite there that says that when I've got double apped onto loop, then I can reduce that to app double loop composed with app double loop. Okay, and so let me just copy this one in. I don't think it's worth typing it all out. Okay, what do we need to do next? Well, by using our general fact about any function apped onto a composite of paths is app of the function on one path and then app of the function on the other path, we can reduce app double on 2 loops to app double on loop composed with app double loop. And then each of these individually should reduce to loop then loop on this side and loop then loop on the other side there. And so that each individually reducing, I'm using this app2 operation, which says that if I have a 2-argument function, then I can put a path on one side, a path on the other side, and get a path between here to here by this, and then here to here by this, and then put those together gives me a path from this whole term to this whole term there. Okay, so what this was supposed to illustrate is that functions are automatically functors, automatically group homomorphisms when we're talking about the group of paths in a type. And so you don't, in the definition of the function, say what it does on a composite, but the rest of the structure of the type theory tells you what it does on a composite there. Okay, I know that was kind of heavy, but does that double make sense? Any questions? Cool. Okay, so what I want to do with the last little bit of class today is to now talk about the 2-point circle. So the 2-point circle, I don't know what to call it because it's also the circle, but I called it circle 2 for circle with 2 points, is going to be a second example of a higher inductive type. And what's happening in the 2-point circle is that rather than just having a point and a loop, we're going to have a point and 2 points, so the north and the south, if you remember the picture from the beginning, along with a west side and an east side, which are both going to be paths from north to south. And so what we can think about doing is then saying, okay, if this is supposed to be an different but equivalent presentation of the circle, then how do we map the circle we defined before to this one and vice versa? Because if you remember the last lecture on equivalences, an equivalence is determined by maps between the type that compose to the identity. And we'll mostly work with the definition of isomorphism that you saw in the Agda exercises sheet, where we just work with maps back and forth to a map and inverse and homotopies between them. But that can be improved.
And there's a very good question. Why
okay.
don't you use a rewrite rule to have definitional computation rules for the loop constructor for S1?
That's a good question. You could. I think, let me not try to do it live, but I think you could. One reason is that, like, it's in practice, in my experience, doesn't end up saving you all that much anyways, because you'll end up with like these things of like massaging an app along a composite as being explicit proofs anyways. And so then by the time you're doing that, like, it's not that hard to apply these. In cubicle type theory, like a bunch of these, not this one, but a bunch of more things are definitional, and in that setting, it's really helpful to have it. But also historically, I think it's because when higher inductive types were first invented, I don't think people thought, well, I don't think people knew that having that as a definitional equality was compatible with the models. I'm not totally sure on the question about that, the current status of that right now, but it was to give slightly more models by not having a definitional equality there. But the other thing is, like, yeah, I'm not sure that in general it helps too much, because now that we've got higher inductive types, and like you'll be doing a bunch of path algebra anyway. Good. Okay, cool. So 2-point circle is supposed to have a north, a south, a west side, and an east side. And so what did I call it? Let's write a map 2, which takes S1 to the 2-point circle. So what does, how do we do this? Well, if I want to map S1 into anything, then what I need to do is I need to find a point in that type and a loop in that type. So what point should I pick? Well, I've got a choice, right? I could pick either north or south. Let's say I pick north. Now I've got to find a loop in circle 2 that is a path from north to north in circle 2. So I can't exactly pick, say, east if I'm going clockwise, right? Because east is a path from north to south, whereas what I need here is a path from north to north. But what I could do is I could go down along the east side and then back up along the west side. And that is one particular loop on the circle. So there's a function from the circle with 1 point to the circle with 2 points, which sends the base point to north, and then sends the loop to going clockwise around the clock from 12 o'clock. And you could pick other things, right? Like there's lots of other paths you could pick here if you wanted to define different functions there. And so if we want to go in the other direction, then what we need to do is that we need to map out of the 2-point circle. And to map out of the 2-point circle, what we need is a 2-point circle induction principle or non-dependent elimination principle or recursion principle, which I'll copy in here, which says that if we're mapping out of the 2-point circle, then, well, for the 1-point circle to map out of it, we found a point and a loop in some type. The 2-point circle is the type generated by a north and a south and a west and an east. So to map out of it, if it's supposed to be the least type generated by that data, the free type on those constructors, then to map out of it, what you need is a north in the type X, a south in the type X, a west in the type X, and an east in the type X, where west is a path from that to that, east is a path from that to that, and then you get a map from the 2-point circle there. So the general principle of higher inductive types is to map out of them. You just say where each constructor goes. 1-point circle had one point constructor base, one loop constructor loop, you've mapped those into X. 2-point circle has 2 point constructors, north and south, 2 path constructors, you find those in X, and then that gives you your map there. So if we want to do a map from the circle to S1, then we could do that. And so now we've got these 4 things to figure out. We've got the 2 points of S1 and 2 paths of S1. And so for the points of S1, there's kind of not much choice because, well, S1 only has 1 point constructor. Now we need 2 paths in S1. And so, of course, you can, fill in any of the paths from base to base here that we've considered. But if you want this function to be inverse to the one that I defined there, the 2, then what we're going to want to fill in is, for example, that when going along the east side, let me see how I did it in the notes. When going along the west side of the 2-point circle, you stand still. And when going along the east side of the 2-point circle, you go all the way around the loop. Okay, so this is kind of like changing the tempo as which you walk around the circle. As you're walking around just one side of the 2-point circle, you walk around the whole circle. And then when you're walking around the other side of the 2-point circle, you just stand still because you're already there. And let's see. Now, what we could check, for example, is that okay, not quite that yet, sorry. Okay, what we could check, for example, is that these functions are sort of mutually inverse in one direction, or I guess inverse in one direction on the constructors. So for example, if I want to say that if I first go from the 2-point circle to the 1-point circle and then go back to the 2-point circle, it sends north to north, then what I want to do is reduce the two functions that I just defined, the S1 rec and the circle rec, on the constructors, right? Because this is applying this to north, and have that reduce. So to get that to reduce, I need to put in all the reduction rules for the elimination rule for the 2-point circle, which are exactly analogous to what we did for the 1-point circle, right? So there's a reduction rule that says when you apply a elimination to north, you get in the N thing you put in. When you apply an elimination to south, you get the S thing you put in. When you apply the, do the app, turn those into rewrites. When you do the app on west, you get the west path you put in. When you do the app on east, you get the east path that you put in. And so then, for example, we can check that this one just definitionally reduces. From north is base, 2 of base is north. And so from north to north is north. Okay, for from south is, let's calculate it. From of south gives you base, 2 of base gives you north. So when you round trip this, you get, right? We don't actually get back where we started here. 2 of from of south is not actually definitionally south, it's actually definitionally north. But if our goal is to construct a path here, not a definitional equality, then we can put any path that we want in here, like, I don't know, west or something there, is a path from north to south. So when we're proving that these functions are mutually inverse, we're not just saying that the definitions, if you expand them, take you back where you started. We get to put in a path here. We get to put in a homotopy if we need to. And that'll be fine for showing that these two types are equivalent for a reason that we'll talk about next time. Okay, so since we're running out of time, let me just copy one in and we'll read it. And then you can read the other in the notes. Okay, so don't worry too much about the proof terms over on the side there. If we ask that the round trip, do the from to get from the 2-point circle to the 1-point circle, do the 2 to get from the 1-point circle to the 2-point circle, then is coming back as west, that that this composite takes west to west, which is what we would want if this was an inverse, then that actually won't type check, because of the fact that 2 sends the round trip from then 2 sends south to north. But the right thing to do will turn out to be to adjust that by this path that we put in here and say that, oh, it doesn't come back to west, but when you compose it with this path that we came up with here, it does come back to west. Why is that the right thing to do? We'll talk about the dependent eliminator for the circles next time, and that'll tell us why that's the right thing to do. But if you do that, then you can calculate that from then to adjusted by this thing actually gives you west. And the reason is just this is west. And if you naively calculate from then to, then from the map from the 2-point circle to the 1-point circle sends west to reflexivity, and app by definition sends reflexivity to reflexivity, and app by definition sends reflexivity to reflexivity. So you get a reflexivity in this term, and then composing that with west gives you back west. So I expect this to be a little mysterious at this point, and it's not super important that you get the details. But next time, when we do the dependent elim, we'll talk more about like why this is the right thing to do. And so, oops, sorry, accidentally closed Agda there. Control X, Control C. So, but anyways, that was kind of the end. Let me reopen it just so we can look at it. But Okay, so the other things in the notes file are definitions of the other types that I drew pictures of at the beginning, like, for example, the torus here, where it's got a point, two paths, and a square, which says that the two paths commute. And then the torus eliminator says that to map out of that, you find two paths that commute. And for the exercises that we've got for you for this time, a lot of them, so like this first chunk and this chunk, well, actually that one's kind of hard. This isn't the version with the chili peppers, but that one's a chili pepper. A lot of these are sort of very directly based on the stuff that we just talked about. So like this is all just like doing stuff with S1 and path algebra and stuff like that. And then the other direction, calculating the other direction of the circle inverse thing that I just did is actually, I think, easier than the one that I showed in lecture because it doesn't involve that adjustment thing there. So that one, you can look at doing that. And then here I put a bunch of kind of harder exercises. These are all chili pepper ones for you to do if you really want to play with some harder stuff. But this uses the torus, which we haven't really talked about yet, and suspensions, which we haven't really talked about, and push-ups. So like, you know, if you're doing some exercises and you get through this part, then I think that's excellent. And if you even get through like a few of these, that'll be enough to do the next lecture. So it's not, you know, feel free to stop way early, like, you know, don't try to get to the end of the file. Okay, so that's all I got for today. What we're going to do next time, just to preview, is to talk about how you prove things about circles and other higher inductive types. So that's called the dependent elimination rule. And then after that, we'll eventually use that to calculate the fundamental group of the circle. Okay, thank you all for your attention and working on this stuff. It's really exciting to see so many new people interested in this topic.
Great, let's thank Dan. I guess maybe for the sake of the recording, I'll mention that there is a GitHub repository associated with the summer school, and that's a location to find all of these files, the lecture notes, and also the background files, the prelude files, and the exercises. So we're keeping that up to date. Do we want to take any questions maybe from the TAs for the recording, and then I'll turn off the recording? Okay, I think let's end things here. Thanks a lot, Dan. We're looking forward to the remaining lectures in the series.
Okay, thanks.